Let's solve some absolute value inequalities. Of course, what I'm talking about are inequalities that happen to have absolute value expressions in them. Let's take a look at a simple absolute value inequality first, and we'll talk about what it really means and some strategies for solving it. So let's consider the inequality absolute value of x is less than 5. And I want to talk about what this really means. Remember, the absolute value of any number is its distance from 0. So basically, we're looking for numbers whose distance from 0 is less than 5. If you take a look at a number line, that means that we're looking for numbers that are less than 5 on this side. But there's also numbers over here that are less than, that have a distance from 0 less than 5. So essentially, this graph is numbers over here that are less than 5 and numbers over here that are greater than negative 5. Now we've seen this graph before, right? That's a between type graph, and we know that that corresponds to an and compound inequality. And then we write the solution like this. The expression is negative 5 less than x less than 5. If we're going to write it using the word and, we'd write x is less than 5 and x is greater than negative 5. Now, what's interesting is that just like our absolute value equations, we split the original inequality into two inequalities without the absolute value bars. In one of them, we simply write down x is less than 5, very similar to what's written up here. In the other one, we change the 5 to a negative 5, but notice what happens to the symbol. And so for all of the less than inequalities, that's what's going to happen. We're going to have x is less than 5, or whatever the value is, and then x is greater than the opposite of 5, which is negative 5. And I'm writing it again just to send home the point that we're splitting these things into two parts, just like we did when we had the equations. So that's going to be our strategy the whole time, right? We're trying to find values whose distance from 0 is less than 5. And that's going to hold true as long as what we're talking about is simply the absolute value of x. Let's try one. So let's find the solutions to the absolute value of x is less than or equal to 7. Well, just like that last problem, we're basically talking about values whose distance is less than or equal to 7, distance from 0. And so there's two ways to write this answer. We don't have any inverse operations to do. We just have to interpret it the same way we did the last slide. This is going to be 7 less than or equal to x less than or equal to 7. I should have said negative 7 on that side. Negative 7 less than or equal to x less than or equal to 7. If you want to write it with an and, you'd write x is less than or equal to 7 and x is greater than or equal to negative 7. And notice again we've broken it into two inequalities, right? We put the word and in between it. Now, inequalities that look like this aren't very interesting and they don't show up very often, so we're going to start to add more operations to the scenario, and then we'll have to solve those as well. Let's take a look at another example. So here's an absolute value inequality. The absolute value of x plus 3 is less than 12. Before we work our magic with this absolute value, we're going to have to deal with this plus 3. And we know how to do this. We use inverse operations, right? We're trying to isolate x. So we're going to use inverse operations, and we'll subtract 3 from both sides. When we do that, you know these 3's cancel out, and we end up with just the absolute value of x on the left-hand side. And over here, since we subtracted 3, we're going to get what? 12 minus 3 is 9. So now we're down to the absolute value statement. The absolute value of x is less than 9. And we now know that that is going to be split in two pieces. Let's write it with the word and this time. Keep in mind that all these less thans or less than or equal to's are going to have an and in them because they make that graph that's shaded between. So the first solution is x is less than 9. That's the right-hand side of the graph. And the other solution is x is greater than or equal to negative 9. All right, just like we did on that first slide with a 5. If you're going to graph it, I'm going to go by 5s. So we're at negative 9 here. We're just less than. And we're going all the way up to positive 9 over here. So that's the graph of this inequality. Turns out it's just a compound inequality with an and, right? And that less than in there. Let's check out another example. Here we have yet another compound, or not a compound, absolute value inequality. And again, before I deal with that absolute value of x, I want to deal with this 2. It's 2 times the absolute value of x, so the inverse operation is to divide by 2 on both sides. That brings us to the inequality. Absolute value of x is less than, was this 3? And I think by now you know that this is a quick answer. I'm going to write down x is less than or equal to 3. That's the obvious piece. And then I'm going to write down and x is greater than or equal to negative 3. And that's the less obvious answer. But again, we're shading basically all the numbers between negative 3 and 3, and there'll be solid dots. Going by 2's here. Oh, that doesn't make any sense. You can't number it like that. I can't believe I did that. If I put 0 in the middle, I can't have a 1 and then a 3. Let's go 1, negative 3, negative 5, and 3 and 5, right? They all have to be 2 apart. Okay, so I'm at negative 3 filled in, and I'm at 3 filled in. And again, these are all the numbers. When you double their absolute value, it's still less than 6. Less than or equal to 6. Now we end up complicating these absolute value inequalities when we start throwing extra operations in between the absolute value bars. In this case, right now we have x minus 3 inside the absolute value bars. And this doesn't mean the same thing as the absolute value of x. The strategy is the same, but in terms of how it looks on the number line is a little bit different. So I'll explain that in a minute. First, we're going to do what we've been, the operations that we've been performing the whole time, and we're simply going to split this thing into an and compound inequality. So either x minus 3 is less than 4, just like it says, I'm going to say either and, even though that doesn't make sense in English. X minus 3 is less than or equal to 4, and, don't forget this side, x minus 3 is greater than or equal to negative 4. Once you split it into that compound inequality, you can use your inverse operations. We're going to do plus 3 across the board here because it says x minus 3. Now be careful. These guys are gone. I agree. But 4 plus 3 here is 7. And negative 4 plus 3 over here is negative 1. And so this graph, turns out, is not centered on 0. Let's draw this, and I'll show you what happened. So I'm greater than or equal to 1, negative 1, and I'm less than or equal to negative 7. And I'm going to shade this in a minute, but I want to take a look at where the center of this thing is. There are 1, 2, 3, 4, 5, 6, 7, 8 spaces. And what that means is that if I go 4 spaces over, 1, 2, 3, 4, 1, 2, 3, 4, the middle number is 3. So instead of checking to see the values that are 4 spaces away from 0, because this is x minus 3, we're actually checking to see the values that are 4 spaces away from 3, right? All of these are 4 or less away from 3. I'm going to shade this in. There's no circle there. That's just, I was showing you where that center point was. This is all shaded in. So I circled that for note-taking purposes, but not as part of the graph. So that means that this number right here is pretty important. We are asking in this inequality, tell us the solutions who are 4 away from 3 or less, 4 or less from 3. And that shift happened because we plugged that number inside the absolute value bars. If you're not drawing the graph, and all you need is the statement of the inequalities, then you don't really need to know that that means that we've centered it at 3, but it's good to know the structure of these problems and how it's related to the initial one that I showed you. The strategy is the same here. We break it into 2 pieces, one of them where it's just less than or equal to, and the other one where it's greater than or equal to the negative, and we solve them. That's how we did it. So the strategy is the same. This thing down here with the graph, it's just interesting, and it's something to sort of tie everything together. Now, what we need to talk about is the greater than problems, and so that's what's coming next. Yeah, so I know I just said we were going to talk about greater than inequalities, but first let's try one more kind of nasty inequality with a less than in there. It's actually not nasty. We just have to do more inverse operations. So you know I'm going to work on these values here that are outside of the inequality first. In this case, I'm going to do an inverse operation on a plus 4, which is a minus 4 to both sides. You know that crosses these out. And then we're multiplying 3x plus 2 in absolute value bars. That's going to be less than, what is this, 9? 13 minus 4 is 9. I have to deal with this 3 on the outside next. Because it's multiplied, my inverse operation is going to be to divide. That crosses this one out. Now I have this absolute value of x plus 2 is less than 9 divided by 3, 3. Okay, this is the point where we have to break into 2 pieces. The first piece is just x plus 2 is less than 3, just like it says. The other one is and x plus 2 is greater than negative 3. And now I have to solve these 2 pieces. And to do that, it's going to take one inverse operation, which is minus 2. Now just be careful here. On the left side here, I get x is less than 1. On the right hand side here, I get x is, what is this, greater than negative 5. If you were shading on a number line, you'd put a circle at negative 5 and a circle at 1, and you'd shade in between them. But lucky for you, I've run out of space, so we're just going to stick with this written solution and call it good. Now, let's talk about those greater than problems. So I'm going to go back to a simple version of an absolute value inequality. This time, there's a greater than sign. And remember, what we're saying here is that we're talking about the distance from 0. So we're talking about numbers whose distance from 0 is greater than 3. If you look at a number line, 0, 1, 2, 3, 4, 5, so on, so on, so on. If we're talking about numbers whose absolute value is greater than 3, that means their distance from 0 is greater than 3, that's like 4 and 5 and 6 and 7. And let's see, on this side, that'd be like negative 4, negative 3.5, negative 4, negative 5, negative 6, negative 7. Turns out, we're basically shading the ends of the graph, right? The numbers that are bigger than 3 and the numbers that are less than negative 3 are the values that fulfill this inequality. And we've seen a graph like this before. This is just one of those graphs that we made when we had those OR inequalities, those compound inequalities. And so what that tells me is that I can rewrite this problem as an OR problem, and I won't have the absolute values anymore. Basically, this is x is less than negative 3, or x is greater than 3, right? That's the two sides. This picture goes with this one. This picture goes with this one. We've seen these before. This inequality looks almost exactly like the original. And then notice with this one, we flip the sign and we make that second value negative, which again is very similar to the absolute value equations we made. We always had two pieces. One where it looked almost exactly like the problem, and the other one where we made it negative. And in this case, we flipped the sign. And because this is a greater than, and it makes this graph with the arrows pointing away on either end, we know that's an or now. So anytime we break up a greater than problem, we're going to make it into an or problem. Let's take a look. We'll start with a simple one. This is the absolute value of x is greater than 12. And you know I'm going to break into two pieces. One piece looks basically exactly like the original problem. X is greater than 12. That's the right-hand arrow. Right? The other piece is when I flip the symbol around and make the 12 negative. That gives us the two pieces. So these solutions are solutions to the absolute value problem. The thing we have to do though is put an or in the middle, so we union those. And you've seen this graph before. It's a number line with arrows on either end and circles on 12 and negative 12. I won't draw it now to save us some time. But the strategy here is very similar to the less than inequalities. Just don't forget to put the word or in between these guys. Let's try a more complicated problem. So just like our other problems that we worked on, we start throwing in extra operations to see if we can handle them. And by now, I think you'll agree that we can. Here I have the absolute value of x plus 5. And the way we attack that is we subtract 5 from both sides. We've done this for 2 chapters, and we're starting to get pretty good at it. That leaves the absolute value of x is greater than 9, right? 14 minus 5 is 9. And now we're at the point where we need to break this inequality up into two pieces. This is going to be an or problem because it's greater than, and the solutions are simple. This is x is greater than 9, or x is less than negative 9. That's how we get the two pieces of the graph. It really is as easy as it looks. Let's try another one. Now, just like with our less than inequalities, things do get a little more complicated when we throw some extra operations in between the absolute value bars. But I don't want you to panic, because now we have a strategy down. As soon as we get to the absolute value bars, we're going to break into two problems. So the first problem is just going to be x minus 8, and that's just going to be greater than or equal to 6. And then the other piece is x minus 8. And then remember, we flip the symbol, less than or equal to, and we make it a negative 6. Now we'll use inverse operations to do the rest of the solution. This is a plus 8 on both sides. And actually we have to do that on this problem too. I don't know if you noticed or not, but I left off the word or, which is kind of a big deal, so I'm going to put that in right now. Over here I get x is less than or equal to 2, or over here I get x is greater than or equal to 14. And those are the solutions. X is less than or equal to 4, or x is greater than or equal to 14. Now what this would look like on the graph is a circle on 2 and a circle on 14 with arrows going outward. I do want to point out to you that basically what we are listing here are numbers who happen to be 6 or more units away from 8. Anything greater than or equal to 14 is 6 or more units away from 8, and anything less than or equal to 2 is 6 or more units away from 8 also. 8's kind of the center of the midpoint between the two circles that you put on your graph. That's just a little tidbit, an anecdote, if you will. So that's the deal with the absolute value inequalities. Very doable, same old inverse operations. It's just that, like the equations that we worked with, we have to break these into two pieces. And the additional thing to consider is, have we turned it into an or problem or an and problem? Just let me point out that when you have greater than or equal to, those are or problems. And when you have less than or equal to, those turn into and problems. If you can keep that straight, you'll be in good shape. Good luck.